Hey, what's up everybody? This is Ray. Welcome back to our OpenGL ES and GLKit video tutorial series. In this part of the series, you're going to learn about shaders and the graphics pipeline. Here's what the app will look like when you finish this part of the series. As you can see, we finally introduced some color into the mix. So far in this series, you've been using what's called ordered drawing. That means if you want to draw a triangle, you list out the vertex information for the 3 vertices that make up that triangle, and then repeat that for the second triangle and the third triangle, and so on. The problem is this isn't very efficient when you're dealing with vertices that are repeated. Consider the case where you're trying to draw the square shown here. You have the first triangle which goes between vertex 0, 1, and 2, and you have the second triangle which goes between 2, 3, and 0. So if you were drawing this in the ordered manner, your vertex array would look something like this. You'd list out the information for 0, 1, and 2, and then 2, 3, and 0. The problem is you've now repeated the information for vertex 2 and vertex 0 in 2 places because it's used in both triangles. This isn't very efficient, and although it might not seem a big deal for a small simple case like this, the bigger your geometry gets, the more space is wasted, especially as your vertex structure starts containing a lot more data than just the position. So an alternate way to do this is an indexed way. In the indexed way, you have 2 different arrays. The first is the array of vertices, and you just list out the information for each vertice, and then finally you list out the indices that make up each triangle. So 0, 1, and 2 are the indexes inside the vertex array for the first triangle, and 2, 3, and 0 are the indexes inside the vertex array for the second triangle. That is called index drawing, and you have to send your data, your 2 buffers, to the GPU just like you did in the ordered case. The difference is now there's 2 different slots that you need to store this in. So you generate a buffer for both, but you have to map the vertex structure to the GL array buffer slot like you did before. But there's a different slot when you're working with index buffers. It's called GL element array buffer. Index buffers are also called element array buffers sometimes. So you have to map it to that one instead. But the rest of the process works the same. It's GL gen buffers, GL bind buffer, and then GL buffer data. All that differs is where are you binding these buffers. Let's also take a look at what the draw code looks like between ordered and index drawing. So in ordered drawings, you've seen this. You bind the vertex buffer to the GL array buffer slot, and then you call GL draw arrays. Well, for index drawing, it's a little bit different. You still bind the vertex buffer as usual, but you also have to bind the index buffer to the element array buffer slot. Instead of calling GL draw arrays, you call GL draw elements. You pass in the number of indices, and you pass in the data type used for each index and the start point. And then if you use that, it uses the index buffer to look up the triangles to draw from the vertex buffer.
Okay, so in this demo, we currently have the white triangle. And what I want to move is move it to a complete square that fills up this entire screen. But I want to set it up with using both a vertex buffer and an index buffer in order to be as efficient as possible. So let's switch back to rwtviewcontroller.m, and I have the list of vertices here. So let's go ahead and replace these with the ones for the square. So we'll start with the right-hand bottom. Then we'll do the top right. Then we'll do the top left. Then we'll do the bottom right. Now that we have the vertices, let's list the indices of how to make triangles out of these. First is 0, 1, and 2, and final, that's triangle number 1, and triangle number 2 is 2, 3, 0. Let's also get a list of the index count because we're going to need that later. We'll store it in a variable up here. I could just put 6 in here, but let me show you a secret trick to make that a little nicer. If we take the size of the indices array and we divide that by the size of the first element in the array, that will give us the number of items inside the array. This is just a little cleaner because it dynamically calculates the size based on whatever you put in there. Okay, next we already have the code to generate the vertex buffer from last time, and that doesn't have to change. The only difference here is we have to create the index buffer as well. It follows a similar format. First we call GL gen buffers, and we want to store this inside a variable, so let me create one for that. By the way, notice that I could have created an array of buffers beforehand, like up here, and then passed in 2 and passed in the array buffers and did it all at one go. But I'm just creating them separately here so it's easier to understand. Okay, so now we have to bind a buffer, but we don't want to bind it to the array buffer slot. That's for vertex arrays. Instead, we'll bind it to the element array buffer slot. That's the one used for index buffers. And then we can send data with GL buffer data. And you can see here that it's pretty much the exact same line as this one, except we're using the indices and we're using this slot, which is bound to the index buffer. Okay, now the only other changes we need to make is down here. We already are binding the vertex buffer, which is good, but we also have to bind the indices. So we bind it to the element array buffer, and we pass in the index buffer. And then instead of GL draw arrays, let's comment that out, we want to use GL draw elements. GL draw elements means that you're using the index buffer. And we want to use GL triangles again, and the index count that we recorded earlier. We're using unsigned bytes for the indices, and we don't want to skip anything, so we'll start from 0. And that's it. If I run, we now have, actually, this is a box that renders to the entire visible area.
In this part of the series, we want to add some color to the mix. We want to be done with this white triangle and move to a nice rainbow-colored square. To do this, we need to keep track of some additional information for each vertex. Instead of just storing the position, we also want to keep track of the desired color for each vertex. So in this example, we want the bottom left corner to be black, the bottom right corner to be red, the top right to be green, and the upper left to be blue. So to do this, the first thing we need to do is add some new data to our vertex structure to store the color information. And this is just going to be an array of 4 floats. Then we need to modify our vertex data to keep track of the color we want for each vertex. So now that we have this new information inside our vertex structure, we want to pass this to our shaders as input variables. How do we do this? Well, in our vertex shader, we're just going to add another line, just like we did for position, for color. And we're going to say attribute to say it's input variable, vec for a color. Now remember, the vertex shader, it doesn't actually do anything with color. Its only job is to set the position of each vertex. It's the fragment shader that deals with color. So we need to get this color information from our vertex shader to a fragment shader. The way you can do this, there's a way to send data from the vertex shader to the fragment shader. And that's by having a variable that's an output variable for the vertex shader and an input variable called the fragment shader. And the way you do this is by putting varying beforehand. That says that's a input/output variable. And as always, you give it a type, and you also give it a precision. And low p is like low precision, there's medium p and high p. Generally, you want the lowest you can get away with for optimization purposes, and we don't need a lot of precision for this, so low p is fine. And you give it a name, frag color. And then in this simple example, all we're doing is we're setting the output variable to be whatever's passed in as the attribute. Then over on the fragment shader, we declare that same variable, and that's going to be passed from the vertex shader to the fragment shader, and then we set the final color to be whatever is passed in. Now you might wonder, how does this work exactly? Because you might understand how it works if you're coloring the exact same position as one of these vertices. Like if you're coloring the top left, well, okay, it's obviously supposed to be blue, and the top right's obviously supposed to be green. But what about one of the values in the middle? Like in the top upper middle of the box, the area between blue and green. What color should that be? Well, this is actually one of the beautiful parts about how vertex shaders and fragment shaders work. When you have one of these varying values, the rasterizer, which I'll show you where that fits into the pipeline in a minute, is sort of the step right before the fragment shader. And what its job does is it takes those variables that go from the vertex shader to the fragment shader and it interpolates the values based on where the pixel is you're trying to color related to the vertices that are nearby it. So if you have a pixel that's between 2 different vertices, it will find the mix of those 2 values, that's called interpolating, and give you that resulting value that's the mix between those 2 values. So we have 2 colors, red and green, gets the mix between those 2 values, it's kind of a blue-green, and that's what's going to be put out. And that gives you the nice gradient effect that you saw in the picture earlier. Okay, so now that you have like a high-level idea of what vertex shaders and fragment shaders are doing, I want to fit this all together in the pipeline for you so you can understand what happens from the beginning to the end to get something rendered onto the screen. This is the picture that we'll be going through, and we'll be going through this step by step. The first step is the vertex buffer objects. It's sending the data from your CPU to your GPU about your vertices and the triangles that you want to render, and then binding those to be active and saying, go ahead and draw. And we've covered this in a lot of detail. I think you should know this by now. So let's see what happens next. The next step is for each vertex that you've specified, your vertex shader gets called. And this job is to output the final position and optionally do other stuff. Like in this example, we're passing a variable to our fragment shader here. And this is the same code we covered earlier. After the vertex shader, the next step is primitive assembly. And the primitive assembly's job is to figure out all the triangles that make up your geometry based on what you've passed into your draw method. So far we've been usually calling GL triangles. I think we used GL line in one of the challenges and GL line strip, but there's other options available as well. So first of all, there's triangle strip. And that's kind of cool in that the first 3 vertices make up triangle number 1, obviously, but then every vertex after that takes the previous 2 vertices to make the next triangle. So for example, once you put down vertex 3, it will make a triangle out of 3 in the previous 2, which is 2 and 1. And you can put down 4, it'll make a triangle out of 4, 3, and 2, and so on. So it's a more efficient way to make some geometry if you have a lot of repeat use vertices there. Similarly, the triangle fan is another sort of optimization you can use. If you have a lot of vertices going out from a middle spoke, the first 3 make up the first triangle, obviously, but everyone after that connects the previous vertice and the center. So you can go around in a nice efficient fan like that. And a lot of your 3D modeling tools will sometimes do some of this stuff automatically for you. The next step is the rasterizer. So the rasterizer knows that the next step is the rasterizer. So the rasterizer is set up to display anything that's in that 2x2 block centered on 0, 0. And also it knows how big the final screen is, which on the iPhone, if you're on a 4-inch screen, is going to be 320 by 568. So it says, okay, I know this triangle is going to be on the screen, and here's how it maps to what pixels, and what pixels are supposed to be inside this triangle. And its job is to call the fragment shader for each one, and also any variable that comes from the vertex shader that's a varying value, it interpolates it based on the position of that point based on the nearby vertices. So in the example from earlier, if it's at the top area and it's evenly between the upper left and the upper right, well, that would be 50% upper left, 50% upper right's value. And then the next step is the fragment shader, which you've already covered. Its job is to set the final output color. And here it just sets it to be that varying value. The next step is the testing and blending stage. So far in this series, you've only been rendering one thing to the color buffer. But usually in a real app, you'll be rendering a lot of things to this color buffer. So there might already be something in the color buffer, and then you have to blend what you're drawing now on top of what's already there inside the color buffer. And remember, the GL view takes that color buffer and presents it onto the screen. The other thing that happens is the testing phase. So sometimes your fragment shader might be actually emitting a fragment that's outside the bounds of the visible area, in which case that fragment needs to be discarded at this phase. And the final step is the frame buffers, and that's the stage where the GLK view is set up to take that color buffer inside the frame buffer and present it on the screen. All right, it's pop quiz time yet again. I want to make sure you guys understand these stages. So as always, I'll go ahead and read through the questions. Go ahead and pause the video, write down your answers, and then you can play again to see if you got it right. So first of all, please give me the name of the stage in the pipeline that's responsible for making primitives with the vertex and element arrays, setting the position of each vertex, setting the color of each fragment, breaking primitives into fragments and interpolating the values, combining the output with the previous output, discarding fragments outside the screen, and more. All right, go ahead and pause and then play again when you're ready. First of all, making primitives with the vertex and element arrays, that will be the primitive assembly stage. Setting the position of each vertex, that's the vertex shader. Setting the color of each fragment, that's the fragment shader. Breaking the primitives into fragments and interpolating values, that's the rasterizer. Finally, combining the output with the previous output, discarding fragments outside the screen, and more, that's the testing and blending phase. All right, it's finally time to get into the demo. This time we're going to start by adding the extra color information into our vertex structure and updating our vertex data appropriately. Then we'll update our vertex shader and our fragment shader based on what you've seen here. Then we're going to go ahead and take a tour of the shader class, the RWT base effect that I included last time. So it's not so much magic to you, so you understand what's going on. It's not something you really need to rewrite because it's the same kind of thing you do each time, but I want you at least to be able to understand what's going on there. And finally, we will enable the new vertex attribute so that color information is passed through to our shaders.
At this point, we're rendering a white square to the screen, but let's add a little color to this. So we'll start by opening RWT vertex and add in an array of color information. So for each vertex, not only will we store the position now, but we'll also store the color that it should be. So of course, now that we have this new information, let's go back to RWT viewController.m and add the appropriate colors in for each vertex. First one will be black, or red, sorry. Second one will be green. Third one will be blue. And the last one will be black. Okay, so we have this extra color information. Now we need to modify our shaders in order to take this extra color information as an attribute. So going into the Vertex Shader, we're going to add a new attribute for the color. And we're also going to have an output variable for the color as well. It's going to be varying, that marks as output variable. We'll say it's low precision, it's a vector 4, and we'll just call it frag color. And then inside here, we'll just set the frag color equals to the A color. And the rasterizer will interpolate this before it gets to the fragment shader. I'm going to copy this exact same line, go over here to the fragment shader and paste it in. And then I'm just going to set the GL frag color to this interpolated value rather than always being white. Okay, so that's it for the Vertex Shader and Fragment Shader. Next, I want to give you a little tour of RWT base effect because we're going to need to modify it again. So again, the idea behind this class is you give it a Vertex Shader and a Fragment Shader. It's going to compile and link these shaders, and then prepare to draw will do some initial setup. So let's see what's exactly going on there. Also notice that it has a variable here called a program handle. We'll get to what that means in a bit. Okay, so let's switch over to rwtbaseeffect.m. Okay, so scrolling down, here's the initializer. So the initializer just calls compile vertex shader, fragment shader, another helper method. Okay, and here's that helper method. So what this does is it calls compile shader on the vertex shader with the type vertex shader, and then it calls compile shader fragment shader with the type fragment shader. So before I go on to the rest of this method, let's take a look at this compile shader class. It looks like it compiles both of them the same way. So here's the compile shader method. So the first thing we have to do is get the file name of the shader and get that into the actual string with all the shader code, because we send it to the GPU literally as a string. So you might be familiar with this path for resource of type. That's how you get the actual path from a file name of something that's embedded inside your app. So we're getting the path to this shader, whichever one it is. And then to get it as a string, there's a string with contents of file method you can call. And we get it back as an NS string. Okay, next thing, to create a shader, just like when you call GL genbuffers to create a buffer over in GPU land, to create a shader object, you call GL create shader. And you give it the type of the shader in, and that was what was passed in earlier. It's either going to be the vertex shader type or the fragment shader type. And you get back a handle, okay? And the next thing you need to do is, now that you have a handle, you want to send the source across as a string, except OpenGL cannot deal with NS strings. It can only deal with plain old C-style strings. And you can convert a NS string into a C-style string in UTF-8 format through calling the UTF-8 string method, and you can get the length of that as well. So once we have that, we call GL shader source, passing in the handle to use and the string length. So now imagine that object, the shader object that's over on the GPU. Well, it now has the source associated with it. So once you have that, all you have to do is call GL compile shader, and this will actually cause the shader to be compiled at runtime on the GPU. Now, just like compiling your programs you may write, there could be an error in there. So you have to check to see if it has succeeded or failed. And the way you do that is there's a parameter here called, or a function call here called glGetShaderIV. And you can get various status information from OpenGL through this command. In passing in the shader handle and the compile status, you get a value whether it's succeeded or not. And if it has failed, you can use a function called GLShader info log to get sort of some basic error messages that might help you find if you've had a typo or something like that. And if that occurs, I'm just logging this out and exiting, because you should not be having compiler errors in your shader, and it's best to catch them earlier rather than later. And at this point, your shader has been compiled on the GPU, and so you just return the handle back to the calling function. So here we are. We do this for the Vertex Shader and the Fragment Shader. So now we need to link the two, and it's a similar pattern to what you saw earlier. So instead of creating a shader, we actually create a program. A program is a combination of a Vertex Shader and a Fragment Shader. The reason you have to link them is because you have to make sure that the output variables of the Vertex Shader match up to the input variables of the Fragment Shader. So once you create a program, you attach the two shaders with GLAttachShader, and you pass in the handle that you got from those two shaders there. Notice how sometimes it's called handle, sometimes it's called name, sometimes it's called ID. They're all the same thing. It's just the ID for that object. Now here's the interesting part. Remember how I said in the slides that this class is responsible for mapping the name of the variable inside the shader to an index for that attribute, so we can bind it, and so we can enable that vertex attribute and tell the shader where to find that vertex attribute in the vertex array structure. So this is how you do it. GLBind attribute location, the handle, whatever you want to bind it to, whatever index, and then the name of that variable. So right now in rwt vertex.m we just have one, but we need to add another one for this color. So I'm going to add another line just like this for the color. And note I'm not putting an @ behind before the string because it's a C-style string, not a NS string. Okay, so those two, this is basically saying whenever you see a position, that's going to be bound to vertex attribute index 0. If you see a color, it's going to be vertex attribute index 1, and so on. Then you go ahead and link the programs. There could also be an error in that, so you have to use the git program IV, similar before, and use the GLGit program info log to log out any messages. Now, once you're done this, the entire program, consisting of a Vertex Shader and Fragment Shader, will be compiled on your GPU, ready to efficiently be run, and you have this program handle you can use to reference it. And that's where prepare to draw comes into play. So prepare to draw, all it does is it says, I want you to use this program, this Vertex Shader and Fragment Shader when I'm rendering the geometry that I'm about to render. The reason this is important is because you're not limited to only using one vertex and fragment shader. You could have different shaders for different types of geometry that you're trying to render, and that's actually a common thing in a lot of 3D games. And that's really it for this class. So this is the same code we'll be using to run pretty much any kind of shader. The only thing we'll be changing sometimes is binding different attributes and so on. So that's it for this base effect thing. So now all we have to do is move back to rwtViewController.m, and we just need to enable the new attribute and pointer there. So I'm just going to copy these two lines, and let's just update these for the color. So I just updated the number from 3 to 4 because there's 4 components of a color: red, green, blue, and alpha in our structure there. And then I also need to disable it when we're done. So I build and run, and check it out. We now have a colorful square.
All right, that's it for this video tutorial, and as always, we like to leave off with a challenge. I think you'll find the challenge really fun this time. It's to make your own terrain generation class, and you can use this kind of technique in games like Tiny Wings, where you want to create some hills in a dynamic way. We're going to start out really simple and then build up from there. I hope you enjoyed this video tutorial. Thanks for watching, and we'll see you next time.